Okay, so I just wanted to get going with trigonometry today. Some of you, in fact, probably most of you, have done a little bit of trigonometry, maybe in grade 10 or even possibly grade 9. And even if you have your graphing calculator or a calculator handy, you've seen these sin, cos, and tan buttons on there. Again, this might be familiar to some of you, and even if it is familiar, maybe you've forgotten what they actually mean, okay? So I just wanted to talk a little bit. I won't talk very long. I'll try not to about what exactly it is that you're these buttons that you're pushing on the calculator. So the first one that we're going to talk about is the sine, okay, and it's spelled S-I-N-E for the sine function, but we just abbreviate it as S-I-N, and that's typically how you're going to see it. The sine of an angle. So what exactly is a sine of an angle? So these trig functions, sine, cosine, tangent, I can't stress this enough, it only applies to right triangles. That's why I have a right triangle here. We use these sine ratios in right triangles, specifically when we have a hypotenuse. Now that's going to change a little bit later in the week, maybe next week, but for now, I just have a right triangle. And I have an angle here. I called it angle C. I have my points A, B, and I called the point C1 because GeoGebra doesn't like having two different things with the same name. So this is angle C, okay, or point C, whatever. And what I'm going to do here is I'm just going to bring this in and out, and you can see the angles changing. When C is farther away, the angle is more shallow, and when I get closer, the angle is steeper, right? So when I have this angle right here, angle C, I have three sides of a triangle. I have this stands for the opposite side. So this is the side of the triangle that is opposite, that is furthest away from angle C. The hypotenuse is, well, just the hypotenuse. It's the side opposite the right angle. And ADJ here, that's short for adjacent. Okay, so that is the leg of the right triangle, the side of the right triangle that is closest to angle C, okay? And I call this the opposite because it's further away from angle C. So if I go directly across or directly opposite angle C, I'm on the opposite side, the opposite leg of the triangle. Well, this leg right here is adjacent to angle C. It actually touches angle C, if you think of it that way. And the hypotenuse, I know the hypotenuse touches angle C also, but we just call it the hypotenuse, okay? So the sine of an angle, important to remember here, in case you've forgotten, the sine of an angle is the ratio between the opposite side and the hypotenuse. So we need to remember that the sine of an angle is the length of the opposite leg of the right triangle divided by the hypotenuse. Okay? So as this is moving here, you probably notice that the opposite side stays put. I said the opposite length here is 4. Just make it a nice even number. No matter what this angle is down here, angle C, that opposite side stays put. It's always going to be 4. But the hypotenuse changes. As I bring it in, the hypotenuse is smaller. As I bring it out, the hypotenuse is larger. It's longer. But the opposite side is always the same. Okay? And if we remember, in a right triangle, the longest side is always the hypotenuse. Okay? So if I go right here to about maybe 12, if this length here is 12 and that opposite side is 4, remember I'm looking at the ratio. All the sine function does is the sine of an angle. All it does is it gives you a comparison. It tells you what is the ratio of the opposite leg of the right triangle in comparison to the hypotenuse. Okay? How many times shorter, if you will, is the opposite side compared to the hypotenuse, okay? So what I'm going to do here is I'm going to bring this down, okay? And we can see what's going on here. I'm bringing in the angle here. I'm bringing it in a little closer, okay? So, for example, I don't know what the hypotenuse is, okay? But when the opposite side is 4, the adjacent side looks to be 10, okay? how long is the hypotenuse? Well, I could figure it out using the Pythagorean theorem. 4 squared plus 10 squared. 4 squared is 16. 10 squared is 100. 100 plus 16 is 116. So this hypotenuse right here is the square root of 116, whatever that is, okay? What I want you to understand is what the sine function is telling me is it's the length of the opposite side, which in this case is 4, divided by the length of the hypotenuse. And the length of the hypotenuse is the square root of 116, whatever, 10.8 or something like that, for example. That is the number that I get right here, 0.371. So in other words, when my angle is 21.8 degrees, okay, that angle right there, the sine of 21.8 degrees, it's a number. It's telling me what percentage is the opposite length compared to the hypotenuse length. So you can think of this 0.371 as 0.371 divided by 1. Okay, this is like you can think of this as a fraction, this divided by 1. Okay, so what it's saying is when the angle here is 21.8 degrees, the opposite side of the triangle, this length right here, is roughly 37% as long as the hypotenuse. Because remember, it's opposite over hypotenuse, opposite divided by hypotenuse, or 0.371 over 1. So if I were to make the opposite length 0.371, if I were to make the opposite length 0.371, I don't know, it's like down there, and I kept that angle the same, the hypotenuse would be 1. So I'm just going to go back up here to 4 real quick. Okay, so again, when it's 21.8 degrees, this angle, in a right triangle, the length of the opposite side, the length of this side of the triangle is going to be 37.1, roughly, so let's say 37% the length of the hypotenuse. So however long this is, however long the hypotenuse is, that's 37% of however long the hypotenuse is, this opposite length. So what happens when I bring it closer? So when I bring it closer, I'm going to bring it closer now, the opposite side is going to stay at 4. That's not going to budge, that's not going to move. But you'll see that the hypotenuse is going to decrease here. So when I bring it into, how about 5? Okay. When this length is 5, that increases the angle. The angle is now 38.7 degrees. It's a little bit steeper, right? Before it was at 21.8 degrees, but as I bring it in, it gets larger, obviously, and it gets to 38.7 degrees, okay? So what does that say now? Now the sine of 38.7 degrees, what the heck does that even mean? Again, it's comparing the opposite side to the hypotenuse. So now in this case, the opposite side is still 4, okay? It's still shorter than the hypotenuse because the hypotenuse is always the longest side in the right triangle, right? But the opposite side now is about 62.5 degrees. So if I round, I'm going to say 63 degrees, okay? The opposite length, however long this is, which, okay, in this case it's 4, that will be 62.5, or about 63% as long as the hypotenuse. Okay, and I'm going to zoom out here, and hopefully this makes sense. Okay, what happens if I go way far out here, way far out? In fact, I'm going to even go further out to really try to emphasize what I'm talking about here. Look at this angle right here. This angle is super small, right? I'm going to go up to the 40. This angle is 5.71 degrees. Okay, it's a really small angle. The opposite side is still 4, right? But look how long the hypotenuse is now. The hypotenuse is really long. So this small number makes sense because, so 5.71 degrees, what is the sine of 5.71 degrees? Well, remember, you're comparing the opposite side to the hypotenuse. So the opposite side of this triangle, the length of that side of the triangle, is if I round here, this is almost 0.01, right? Or that's about 10%, almost 10%. If I move the decimal 2 places, it's 9.95. I'm going to call it 10. The length of this opposite side of the triangle, opposite angle C, is, oops, sorry, undo that. This opposite side is only about 10% as long as the hypotenuse, because we're comparing the opposite side with the hypotenuse. This opposite side, I could probably fit just about 10 of these opposite lengths will fit on the hypotenuse. So there's 1, there's 2, there's 3 opposite sides, 4 opposite sides, 5 opposite sides. I could fit about 10 of these lengths here on the hypotenuse. Okay, and when I get really close, I'm gonna zoom in real close here. I'm gonna get even closer. All right. What happens when I get really, really, really close? Remember, this opposite side is 4. That doesn't change. What happens when I get really close? Really close, really close, really close. How about like right there, right? I'm really close. It's still a right triangle. It's still, this is still 90 degrees. This is the adjacent side, right? The hypotenuse is still the longest side. It always will be in a right triangle. But when I get really close, when this angle is 82.7 degrees, it's really steep. This opposite side here, it's still 4. We're comparing the opposite side to the hypotenuse, the length of the opposite side to the length of the hypotenuse. This ratio is almost equal to 1 because these are almost equal. If the opposite side were the same as the hypotenuse, it would be the same number. It would be a number divided by itself, which would be 1. But that's not quite the case here. So this opposite side is about 99.2% the length of the hypotenuse, or almost as long as the hypotenuse, almost as long. 99.2% as long. And you can probably guess what happens when that angle gets closer to 90 degrees. When this angle C gets closer to 90 degrees, look what's happening. The opposite side is almost exactly the same length as the hypotenuse. That's why this ratio, it's a fraction, is almost 1, because you're almost dividing a number by itself. And sure enough, when I get to 90 degrees, now this is a round. I know you can see it jumped up here to 1, but that's because I'm rounding to 3 significant figures. Okay, so it says 1 right here, but it's not, because I'm rounding to 3 significant figures. Okay. I can even watch. I'll even change it here. How about 15 significant figures? Look at that. You can see it's not quite run. So don't worry about it. You're never going to have to go to 15 significant figures, okay? But I'm just doing it to illustrate the purpose here. What happens when that angle gets closer to 90 degrees? That ratio is getting closer and closer and closer to 1 until eventually we get to 90 degrees. I wonder if it'll actually touch 90 degrees. Oh, it won't. It goes over. Okay. So it's important to remember that you can see what's going on here. So let's not forget it. The sine of 90 degrees is going to be 1. Okay. I'm going to take this, round this off here. Back to 3 significant figures. The sine of 90 degrees is 1 because when you're at 90 degrees, you can see when you're at 90 degrees, when this gets closer to 90 degrees until we actually get to 90 degrees, the hypotenuse is the same length as the opposite side. In fact, we don't even really have a triangle, do we? But if we did, the hypotenuse would be the same length as the opposite side. There you go. And it's saying sine of what? Because it's not recognizing that there's a triangle. Okay, but there's that nice ratio 1. So moral of the story is the sine function compares the length of the opposite side to the hypotenuse. Opposite divided by hypotenuse. Okay.